Welcome to The Explainer. Today, we're going to dig into how computers do something that seems like magic, how they go beyond just knowing words to actually understanding the structure of what we say. And it's a story that's way more about elegant design than it is about brute force.
I mean, think about it. We do it all day, right? We ask our phones for directions, tell our speakers what song to play. But when you say, "Find restaurants near me," how does that little box of electronics know that me is the center of the search and restaurants are the things it's supposed to be looking for? Well, it all comes down to understanding structure. You see, the first big idea you have to wrap your head around is that language isn't just a flat string of words, one after the other. Nope. It's actually a hierarchy, a deeply nested structure, kind of like those Russian nesting dolls. And to really get that, we need to talk about a core concept from computer science.
And that concept is called recursion. Now, in simple terms, it's just a way of solving a big problem by breaking it down into smaller, identical versions of itself. If that sounds a little, abstract, don't worry. There's a perfect analogy you use every single day.
Just think about finding a file on your computer, right? You open a folder, and inside that, there might be more folders. So you open one of those, and you keep going deeper and deeper until you find what you're looking for. Every time you open a folder, you're doing the exact same thing. Look inside this thing, just at a new level. That is a recursive structure.
And this is why that structure is so critical. Look at this. A simple bag of words approach, which just looks at the words present, sees dog bites man and man bites dog as the same thing. They've got the same words, right? But as structural analysis shows two completely different realities. The meaning, the whole who did what to whom, it's all locked up in the grammar, not just the words themselves.
Okay, so if structure is the absolute key, how in the world do we teach a machine to actually see it? How do we get from just plain old text to that rich, structural understanding we've been talking about?
Well, the answer for a long time has been a process called linguistic annotation. For decades, linguists and computer scientists have been painstakingly adding these little descriptive labels to text, tagging words, connecting phrases, and basically drawing out a detailed, machine-readable blueprint of a sentence's grammatical skeleton.
And this is not a new field, not at all. It actually got started way back in the 60s with projects like the Brown corpus, and then it really took off in the 80s and 90s with things like the Penn Tree Bank, which created this enormous data set that so much of today's natural language processing is still built on.
And here's the crucial part. This annotation isn't just one simple layer of tags. Oh no, it is a rich, multi-layered process. We're not just saying, that's a noun, that's a verb. We're mapping the entire sentence structure. We're labeling the names of people and places. We're figuring out the semantic roles and even tracking who he or she is referring to across a whole paragraph.
Okay, so with that foundation in place, now we can zoom in on a specific group of researchers who are taking this whole structural approach to its absolute extreme.
Let's talk about the Delphin Consortium. Their goal is not just to get a fuzzy idea of what a sentence means. They are all about what they call deep linguistic processing, getting to a super precise, formal, and actually computable representation of meaning. So what's their main tool? It's a powerful framework called Head-Driven Phrase Structure Grammar, or HPSG. You can think of it like an incredibly detailed, exhaustive instruction manual for a language. It defines not just the parts of speech, but all the complex rules about how they can, and, more importantly, how they cannot fit together. And the final output from that HPSG engine, the thing it produces, is something called minimal recursion semantics, or MRS. This is the prize. It's a formal representation of the sentence's meaning that a computer can actually work with, that it can use to reason. I know that all sounds pretty theoretical, so let's make it real. Let's take a look at how their super detailed Spanish grammar tackles a really tricky part of the language.
So the puzzle here involves these little things called clitic pronouns. They're these little unstressed pronouns like me or de or lo. And the tricky thing is, they can either stick to the end of a verb or jump to the front of a whole verb phrase. Getting the rules for where they're allowed to go is a classic challenge in linguistics.
And here it is. This is their solution, and it's brilliant. What you're looking at is called a parse tree.
It's the grammatical blueprint for the Spanish sentence for I have bought you a gift. And you see how it's not just a flat line of words? It's a hierarchy. You've got the main sentence at the top, which breaks down into phrases, which then break down into words. This structure shows, with mathematical precision, exactly how that tricky pronoun te connects to everything else, solving the puzzle perfectly.
So how do they get to this level of precision? Well, get this. Their grammar for Spanish doesn't just have a few categories for words. It has 516 distinct lexical types, each with its own very specific set of rules. I mean, that's the insane level of detail we are talking about.
All right, so at this point, you're probably thinking, okay, this is amazing, but we've got these massive AI models now that seem to get language pretty well. Why go to all this trouble? And you know what? That is a fantastic question. Well, one huge reason is efficiency. Because this whole approach is built on explicit rules, it lets you use some really clever shortcuts. So instead of trying to apply that massive grammar with 516 types to every single possibility, they can first use a simpler grammar to quickly sketch out the most likely structures. Then they filter out the impossible ones, and only then do they bring in the big, powerful HPSG analysis for the few that are left. It's just smart.
And the payoff for all this precision is enormous. It lets us create gold standard data to train all those other big AI models. It enables high-stakes applications like question answering systems where being close enough just doesn't cut it. It improves machine translation, and it even helps us, as humans, refine our own scientific theories about how language works. It's really the bedrock that smarter AI is built on.
Which brings us to our final thought. As the world of AI seems totally focused on just building bigger and bigger models, this deep structural approach forces us to ask a really fascinating question. Is just having more data and more computing power, brute force, enough? Or is a genuine, precise understanding of structure the real key to building machines that don't just mimic what we say, but truly, finally understand it?